Hello, we will be discussing our 6808 project, Distributed Ultrasonic Sensor Network for Tracking Flow of Shoppers. My name is Niall, and with me are Gabriel and DeMarcus.
Our project was inspired by recent events concerning the coronavirus outbreak, namely, how to reduce the risk of transmission in grocery stores and other shopping venues. Coronavirus can live on surfaces, including plastics and metals, for up to 72 hours. One policy we saw some popularity was designating a special shopping period for the elderly. Often, before the shopping period, stores clean their surfaces. With this, we were wondering if instead of setting one specific policy, is there a way we can monitor activity within a store in order to make smarter decisions on when and where to clean? With this, our problem became, how can we gather information on the flow of shoppers in a store while maintaining privacy in a cheap and scalable manner? Our project faced many of the same constraints as other IoT devices we've seen in class. As we didn't want our device to be dependent on proximity to an electrical outlet, battery usage became one of our primary constraints. Since Wi-Fi is power intensive, we had to consider trade-offs between data upload frequency and data availability on the server. Memory usage was another one of our constraints, as we can only store and process on the information we need to. Cost and size were additional constraints that guided our approach.
Here, we have a high-level system diagram. At the ends of each aisle of the grocery store, we place one of our sensor nodes, consisting of two ultrasonic sensors connected to a Wi-Fi enabled Arduino. These sensor nodes track shoppers as they walk by and communicate this information with an AWS server via Wi-Fi. The server does additional processing on this information and makes it visible on a website in a heat map. Our sensor nodes consist of one Arduino Uno Wi-Fi Rev 2 with 6 kilobytes of on-device RAM. This ties into one of our key design constraints, which is limited storage. We connect this Arduino with two sub-$5 ultrasonic distance sensors, which tie into one of our other design constraints, maintaining a low cost. Finally, this is all powered by a 5,000 mAh USB power bank. As someone walks by a sensor node, the node alternates between sampling from the left sensor and sampling from the right sensor. This is done to avoid interference if both sensors were sampled at the same time. The Arduino interpolates the measurements to fill in these gaps and applies a low-pass filter to ignore measurements over the manufacturer-provided 400 centimeter limit. We use a 10-second period of data to illustrate the multiple steps of the algorithm. Next, the Arduino computes the difference between the left and right sensor readings. This will be the basis of the remainder of the algorithm. The first step is to determine when somebody walks by. We call this an event. We calculate the change between subsequent difference values. Here, you can see two instances of when somebody walks by. An algorithm based on the change in difference values identifies when an event occurs. Here, the dotted lines represent the algorithm-identified start and end of this event, which occurs around 7 seconds. Now that we know when the event occurs, we go back to the difference between the left and the right sensor readings and compute a moving average over the event to smooth the curve. Next, we resample this data to contain 40 measurements, which will be necessary as we later compute a dot product. We then scale the data to be from -100 to 100 to accentuate any movements in the data. Lastly, we compute a correlation between this scaled data and a right-to-left benchmark, which is the dotted line. In our experimentation, we found that when an individual walks from the right to the left, the data starts by going up, doing something in the middle, and going down at the end. Here, the correlation is negative, which means that the individual is walking from the left to the right. All of these steps are done on the Arduino in real time in order to maximize the efficiency of on-device storage.
To complete our sensor network, we built a backend using AWS. When the Arduinos go to submit data, they connect through a CloudFront instance to a Lambda function, which just allows them to submit data into our database. When users want to actually query this data, they use another CloudFront instance that loads up a static website. This static website is able to access our backend and displays the heat map that users are able to see. With that, let's jump into our demo. Given our starting constraints, it was very clear to us that we should have precision and recall, battery usage, and memory usage as our three evaluation metrics.
Here, we show the results of various on-device sensor processing algorithms that we tried to implement. The first attempt was the peak finder algorithm, which uses a finite state machine to attempt to detect peaks in the difference between left and right measurements. The second attempt was the naive algorithm, which assumes that if an individual is walking from right to left, the right sensor will change by over 30% before the left sensor changes. The correlation algorithm is the one we discussed earlier. You can see that the peak finder algorithm had very poor performance and failed to identify most of the events. The naive algorithm had much better results, but due to its simplicity, sometimes mislabeled the event. The correlation algorithm had 96% precision and recall.
As far as battery life goes, we compared versus four scenarios. The first of which is the Arduino doing the interpolation on board and sending time and interpolated sensor values to the server. The other is the Arduino just sending time and raw sensor values. Yet another is the Arduino actually doing the analysis on board and sending the time and correlation values. And lastly, the Arduino doing the analysis on board and setting the time and label values. As far as our first metric, which is the earliest time to send to the server, we found that scenarios 3 and 4 were vastly superior. In scenarios 1 and 2, it just ended up being such a deluge of data that it has to send very quickly. We found the same trend to occur under battery life. In that sense, scenarios 3 and 4 were greatly superior. Now, if you'll notice, scenario 4 is actually slightly better than scenario 3. But unfortunately, this actually loses us quite a bit of data. By including the correlations, we're able to have some sense of the likelihood of a particular direction, and that enables us to be a bit smarter on the back end.